Nitrogen is a key element, and its environmental cycling can have a significant impact on ecosystem function. Excess nitrogen sources like agricultural runoff can fuel dense vegetation growth on land, but also contribute to hypoxic dead zones in lakes and oceans. At the East River Field Site's mountainous headwater catchment in Colorado, teams of scientists led by Berkeley Lab and supported by the Department of Energy are working to identify major sources of watershed nitrogen inputs and its fate within the environment. Their goal is to use this pristine natural laboratory to understand where, when, and how nitrogen enters the system and how it is exported during river, soil, plant, and bedrock processes. In mountainous watersheds, ecosystem productivity is often limited by nitrogen availability. Plant and microbial communities depend on nitrogen's various forms to optimize metabolic growth processes that control biomass production. Research at the East River suggests that subsurface nitrogen pathways are activated at different times and in different ways, leading to a two-nitrogen world hypothesis. In the shallow subsurface, snowmelt drives soil microbial activity, causing a large but short-lived release of nitrogen bound within microbial biomass that coincides with the springtime awakening of plants. Varying seasonal patterns have led to earlier snowmelt or fall springs that cause peak nitrogen export to occur earlier and potentially before plants have fully awakened for the growing season. Later in the season and deeper below ground, a second nitrogen world is at play. Here, water tables rise with infiltrating snowmelt and fall during dry summer months. As fluctuating groundwater levels interact with geologically ancient nitrogen-rich Menko shale, chemical weathering can release organic and inorganic nitrogen. Observations suggest that this shale-derived nitrogen pulse is far larger than previously recognized and could contribute a significant fraction of total nitrogen exports. How do changes in snow accumulation and snow melt timing influence the fate of nitrogen and watershed subsystems? What role do the shallow and deep subsurface nitrogen worlds play in system imports and losses? By answering these questions, Watershed Function SFA scientists are bringing new understanding to the key controls on watershed nitrogen cycling and the health of our planet's ecosystems.